Thank you, and I thank the organizers for giving me this opportunity to speak about our work on the TeV detected GRB 1901-14C. So during the conference, we've heard quite a few things about this GRB, but in this talk, I'll particularly focus on the low frequency view of GRB 1901-14C afterglow. So this burst was triggered and located by the Neil Gehrels Swift Observatory with the Burst Alert Telescope in the 15 to 150 keV range, and it had a duration of 25 seconds. There was a rapid follow-up observation with the Swift XRT and the UVOT, where both of them located an uncatalogued source in the X-rays and the optical ultraviolet electromagnetic counterpart. Not only with the Swift band, but this burst was also detected by other high-energy missions like Integral HXMT, Conus Wind, and the Fermi satellite. And the highest energy photon which was detected by Fermi was at 22.9 GeV. Following this, there was a historical rapid follow-up in order to detect the TeV emission from GRB 1901-14C. This was 50 seconds after the bat trigger, which was performed by the Twin MAGIC telescope. In the first 20 minutes of observations by MAGIC, it was revealed that there was a high energy emission at greater than 300 GeVs with a significance of more than 20 sigma. However, after this initial flash of the very high energetic photons, the VT emission quickly faded, which means it was very short-lived. So in this figure, we can see the light curves in the keV, GeV, and the TeV energy bands. This is a paper by the MAGIC collaboration, which is one of the first papers which came out on 1901-14C, and there has been a flood of papers on this particular GRB and its afterglow characteristics. So these, the X-ray is shown by the green bars in this light curve, whereas the violet ones represent the light emission between 0.1 to 10 GeV, and the red filled circles show the MAGIC emission detected in the TeV bands between 0.3 to 1 TeV. The bottom panel here shows the evolution of the photon index with time, and within the error bars, the photon index seems to be nearly the same. Following the TeV emission from this GRB afterglow, there were several multi-wavelength efforts in order to track the evolution of the afterglow, and a series of optical observations were taken with several telescopes. These were some of the early telescopes which were used to acquire the data. Of course, the list is not complete over here. There were more than 24 observatories involved in the follow-up campaign of this GRB afterglow. And with the spectrum, the afterglow spectrum which was taken with the NORT telescope, it was confirmed that the GRB is located at a redshift of 0.42, which is further confirmed with a later spectrum taken with the GTC. And with a Fermi GBM fluence of 4 times 10 to the power of -4 erg per centimeter square, the isotropic energy of the burst was found to be 3 times 10 to the power of 53 erg with an E peak of 1000 keV. So in this figure, I'm showing the E gamma I. So the left figure actually is the E ISO plotted against the redshift, and these are some of the very bright and the energetic GRBs identified with the different missions like the Swift and the Fermi band. So the blue stars here represent some of the brightest Swift GRBs which have E ISOs greater than 10 to the power of 54. Some of them have even less, like this burst over here. And the red diamonds show the GRBs which were located with the Fermi light, again with energies typically greater than 10 to the power of 54 erg. When we place GRB 1901-14C in this plot, the magenta symbol over here represents this GRB, and the energetics of this GRB were around a few times 10 to the power of 53 erg. If you see the bottom right figure over here, it is the Amati plot, the E peak plotted against the E isotropic. Here again, 1901-14C lies somewhere in the middle. It is certainly not one of those very high E iso bursts. This is the optical NIR and radio millimeter band follow-up of the afterglow. The left one is the optical follow-up observations of the afterglow, and the right is taken from several radio telescopes in the centimeter and the millimeter bands. So using our target of opportunity program with the giant meter wave radio telescope located in India, we triggered for observations at 1.4 gigahertz, typically 1 day after the burst, which is represented by this inverted purple triangle over here. And we were unable to detect the afterglow emission at 1.4 gigahertz for this burst at early time. So this is a resultant light curve of the multi-wavelength campaign, which is published by the MAGIC collaboration, which shows the light curve right across the different energy bands and the wavelengths. So early on, starting from the Swift GBM, going on to trace the X-ray, the TeV, and the optical afterglow with several telescopes. So these TeV, as you can see from the figure, that the MAGIC TeV detection is only in the early afterglow phase. And as I said in one of my earlier slides, that typically 20 minutes after this, the emission faded. So in this, it was proposed that the temporal profile, that the sub-T, from this temporal profile, it was suggested that the sub-TeV emission originates in similar conditions to the X-rays and the GeV emission in the forward external shock. We used our facilities to trace the low frequency view of 1901-14C afterglow in the optical with some of our telescopes starting from 16 hours after the burst up to 25 days after the burst, and in the radio bands using the ATCA, the ALMA in the millimeter bands. The ATCA observations lasted from 1 day to 140 days after the burst, whereas the ALMA observations in the millimeter, sub-millimeter bands ranged from 1 day to 45 days after the burst, and the very low frequency observations at 1.4 gigahertz, 650 megahertz lasted from 2 to 68 days after the burst. So using all these observations ranging from the optical to the radio millimeter bands, we constructed the multi-wave band light curve for this afterglow. The gray points here represent the X-ray light curve. The filled circle represents our data over here, and the light shaded data represents the data which is taken from the literature for the afterglow of 1901-14C. So using our multiband observations, we plotted the spectral energy distribution and performed the joint multi-wavelength split in order to estimate the extinction suffered by the optical NIR afterglow of this burst. And from our observations, we were able to identify that this burst suffers a significant amount of extinction with AV value of typically between 1.4 to 1.9 magnitude. So this is also suggested in the MAGIC paper using the optical spectroscopic observations that the burst has a high extinction. But below 10 to the power of 15 hertz, all these different models, the LMC dust, the Milky Way dust, and the SMC dust, seem to agree well with the data. It is only after 10 to the power of 15 hertz that these three extinction models deviate. So using this extinction, we compared the afterglow of 1901-14C, and this is a comparison of the X-ray light curve of this afterglow in the context of other X-ray afterglows which are observed with the swift XRT, and all of these light curves, all of these GRBs have a known redshift. So what we can see here is that the X-ray afterglow of 1901-14C at early times is brighter than the sample of the light curves which have been plotted over here, and typically at late times it is more or less similar to the other afterglows which we see over here. These are the optical light curves in the R band. The left panel is the observer frame light curve of 1901-14C. So the afterglow at early times is typically brighter than the rest of the GRB afterglow optical light curves that have been plotted over here. For comparison, we've also shown the optical light curves of the other two TeV detected GRBs. There's a talk on 180720B in this session itself, so I'm not going to focus more on this first. And the low luminosity GRB 190829A seems to have a rather faint optical light curve over here. So once we shift these light curves to Z equals to 1 frame, which is seen in the right figure over here. So instead, in spite of the large extinction that has been observed in 1901-14C afterglow, the light curve behavior is similar to the afterglow light curve of the other GRB light curve here. However, at late times, this becomes significantly brighter. If you see over here, typically after a few days, this afterglow of 1901-14C seems to be brighter than the rest of the sample.
3 minutes.
In the optical and the radio, in the radio bands, the millimeter and the submillimeter bands, we see the afterglow follows this trend over here and seems to be a pretty normal afterglow as compared to the rest of the sample. When we followed we performed a multi-wavelength modeling of this afterglow, we found that it does not conform with the standard closure relations, and it is a challenge to the standard fireball model. So we performed several tests and identified that a standard afterglow model would not be suitable to explain the evolution of this afterglow. What we saw is that the observed temporal slope in the X-ray bands was 1.34, whereas in the radio band, this was around 1.07. And when using these temporal indices, when we estimate when we identify the theoretical predictions using the closure relations, they were found to be much more steep than those predicted from the theoretical model. And specifically, the slope beyond 10 days is steeper than observed.
2 minutes.
So which would not be useful to model this afterglow with the standard forward shock model. So we invoked the time evolving shock microphysical parameters in order to explain this GRB. We fixed the electron energy index P to be equal to 2.01, and we used the time evolution for the epsilon B and the epsilon E parameters over here, and performed the afterglow modeling using the multi-wavelength data both in the ISM and the wind model. This plot here shows the afterglow modeling results for the ISM kind of environment and the fitted parameters as well as the derived physical parameters. And in this, this seems to be following quite well. So with what the data is showing us, and also the wind model does not deviate much. So there is a little we can say to distinguish both the ISM and the wind model as well as the parameters that we have obtained. So in summary, I would like to mention only a few points, which is that 1901-14C is one of the GRBs which has shown the VHE emission, and the detailed study of the VHE emission, which is presented by the MAGIC group, and the multiband emission, which we've seen over here, that it indicates that the high energy photons arise from the upscattered synchrotron photons, and the evolution of the multi-wavelength afterglow, it does not satisfy the closure relations which are expected under the standard fireball model. And so we require the change in the microphysical parameters, or the parameters to evolve in time, in order to explain the afterglow evolution of 1901-14C. And this fireball, the time evolving microphysical parameters were also used in the past to explain a few other GRBs, which I would like to stop here. Thank you.
All right, thank you very much.